Okay, so this video is going to talk about a shortcut for getting the valence electrons and then a shortcut for writing the formula for the ionic compounds. But remember, always remember that the ionic compound is not a real bond. It's an interaction between a positively charged ion that was a giver of electrons and a negatively charged ion that was the taker of electrons. We are going to refer to the positively charged ion as a cation and the negatively charged ion as an anion. And you'll see something when you move from left to right. We're not going to worry about the transition metals right now. We're going to see that as you move from valence electrons that are S1, S2 to S2P1, S2P2, S2P3, S2P4, S2P5, S2P6, that we increase numerically in the number of valence electrons. That is, everybody in this row has one valence electron, or one dot. 2, 3, 4, 5, 6, 7, 8, with the noble gases other than helium ending in N, S2, N, P6, N being 1, 2, 3, 4, 5, generic energy level. So that magic number of 8 comes from this, that ending S2P6 in the photoelectron spectra. So let's look how that would play out in an actual problem. Okay, so if we had something like aluminum oxide, the first thing to notice is that when we start writing names like this, the taker of electrons, or the nonmetal, we're going to change this to I. So oxygen, oxide, sulfur, sulfide, nitrogen, nitride, etc. So we look at aluminum. Aluminum is in that S1, S2P1 category. So it has 3 valence electrons. 1, 2, 3. Okay. Now if you notice, would aluminum rather lose 3, okay, or would aluminum rather gain 5? And it turns out it's much easier for it to lose 3. So aluminum's charge is always 3 plus, okay? It would much rather lose 3 to be like Regina. You already know that. Oxygen, 1, 2, 3, 4, 5, 6, S2P4. So would oxygen rather lose those 6 or gain 2? Well, we know that it needs to gain 2 to be like Regina. So we know that oxygen's 2 minus. Now, in the past, what we were doing, we're drawing arrows to show all this, and that's fine, and that's showing the transfer of electrons, but that's a little bit too much. What we can do is we can simply balance this like we would in math. Well, what's the common multiple between 3 and 2? It's 6. So we simply can multiply aluminum by what we need to make that 6, which is 2, and multiply oxygen by what we need to make that 6, and that's 3. And there's the balanced compound. You might notice that a trick is just switching them. But you want to be aware, if this was plus 3 and that was minus 3, you don't need to switch them at all. Let's do an example of that. So let's say now we had aluminum, nitrogen, or nitride. And it's common, we've heard of carbon dioxide or sulfur, sodium chloride, etc. So we know that aluminum has 3 valence electrons, so it's got a 3 plus charge. Nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. So it's easier for it to gain 3 than lose 5. So N minus 3. Okay, so those completely balance out. And when we were doing the arrow version, you would have seen that these would have just transferred and you would never have made this mistake, which is why I started you with that. They perfectly fit. But when we're doing it this way, sometimes people will have the tendency to love this little switch motif, and they'll do this. And that is 100% completely wrong. Okay? So the answer here is ALN. If they're the same number, you don't have to switch them. And let's do one more. Let's say we had calcium chloride, chlorine becomes chloride. Okay. We know that calcium has 2 valence electrons, so that's Ca2+. We know that chlorine has 7, so that becomes Cl1- because it only needs 1. Okay. So what's the balanced compound going to be? Well, if we did it the other way, you would have seen that you would have to bring in another chlorine to accept that other electron. But here, they're not the same, so we can just switch them. We don't have to write that 1. Okay, we don't that. So CaCl2. So beware of switching, though. It's very easy for teachers to want to give students this trick up front, but I want you to be aware of it. The worst thing you can do as a scientist is to write something like, Al3N3. That is ugly, 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 ugly. Thank you very much.